All right, so once again, there's a rather interesting formula on this one, but I'm hoping after we do one by hand, you can kind of help me work through how the calculator may help us not have to do it by hand. Of course, you always can, but this one has a few tricky little parts to it that may cause some trouble. Right? So first we have to take care of a definition to make sure we're all on the same page. I think we are, but it says two samples are independent if the sample selected from one population is not related to the sample selected from the second population. Kind of like the tire one the other day, right? Two completely different tires. There was no way I was going to pull the same from any of them, right? The two samples are dependent if each member, and this is kind of a little bit different here, it says, if each member of one sample corresponds to a member of the other sample. Okay? Dependent samples are also sometimes called pair samples or matched samples. And the ones we're going to deal with today are the dependent samples. Right? And I think it'll be very easy to see that the two examples we do later are actually dependent, but we will talk about it. But I think we kind of have those two words fairly well understood, at least in our own words, hopefully. So let's just make sure. So let's classify each pair as independent or dependent. So here we go, number one, there's two samples. So sample one is the resting heart rate of 35 individuals before drinking coffee. Sample two, resting heart rates of the same individuals after drinking 2 cups of coffee. Are those dependent or independent? Okay, what makes it dependent? There's actually a few terms in there that actually make that, okay, before drinking coffee, then after drinking coffee. Yeah, it's the same individuals, right? Because that's going to give us a much better sample as to what's happening. Because let's face it, if I do 35 individuals before drinking coffee, maybe some of those people just have high heart rates anyways. And then I compare it to completely 35 different other people. Is that going to give me a whole lot of information? Not really, because maybe they all have low heart rates to begin with, right? So that would be very chancy to do that. So the fact that we do the same individuals is very important there, and they are dependent because, again, it is the same individuals. Number two says sample one, the test scores of 35 statistics students, and sample two, test scores for 42 biology students who do not study statistics. Yeah, is there a way that could possibly be changed, or what's some of the key terms there that help us actually make it that way? Yeah. Yeah, who also studies, there you go, who also studies statistics, there you go, that could be it. But the key ones here that actually make it independent are, they're saying right here, they don't study statistics at all. So is there any way to get the same people here? There's just no way at all, right? Because we're saying here they do and here they don't, so there's no way. So that's why those are independent. I kind of thought we had a pretty good grasp of that. All right, this formula here does get to be a little bit of a pain. And so I gave you a little bit room to the left and a little bit of room to the right, a little underneath to kind of explain what all the letters are in here. All right, there are a lot of them. All right. No, there's just a lot of, and some of them are new. Okay, but I think many of you will probably be able to figure it out. Now remember, we are talking about the difference between means in this chapter. That's kind of what we've been doing this whole time. So a t-test can be used to test the difference between two population means, again, the population means, when a sample is randomly selected from each population. To perform a test, each population must be normal, and each member of the first sample is paired with a member of the second sample. So now, earlier they didn't say that they had to have the exact same number, right? But now to use this test, it's saying that each population must be normal, and each member of the first sample is paired with a member of the second sample. And most times the person's going to be paired with themselves, right? I mean, that's the best way to do it, right? And the test statistic is D. Okay, D, obviously, what do you think that stands for here? Difference, yeah, okay. And the standardized test is, or test statistic, is this. Again, why do we standardize it? Yeah, so we have something to compare it to. Obviously, some samples could have a difference of 100. The next sample could have a difference of 2. I have no way of comparing them, right? Unless I can compare them to some same information. And so we have T equals D bar. What do you suppose D bar? Yeah, average difference, or mean difference, yeah, between the paired data. So that equals the mean At least the nice thing is in stats, the same things kind of mean the same things as you go through. It's not like they just change what it means. A hat over it means it's an estimate. A bar over it means it is a mean. And if you want a little formula for it, I can give you one. Add up the differences and divide by n, right? Here it's just n because we are just finding a difference here, right? We're not trying to find, there's no necessarily need for degrees of freedom here. Okay. U sub d, or mu sub d, might be a little bit more complicated. That's the hypothesized. How should I put it? Hypothesized mean of the difference. And what have we been hypothesizing the difference to be a lot in this chapter? 0, right? So a lot of times, what are we going to put there? We are going to put 0 for that. That's what we've been saying. Oh, the null and alternate have been kind of based around it being 0 or not 0, right? And so a lot of times we're going to put 0 there. But remember, in that one section, we did put some other information in there because somebody said, oh, maybe the difference is 900 or the difference is 2 or something like that. And so we would put something there. Okay? I think it's pretty obvious. Based on all the formulas we've seen, we probably know what that is. But remember, that's the one thing that always has that just awful formula, right? And so S here stands for the standard deviation of what in this case? Okay, which in this case is the difference. This is the standard deviation of those differences. Is it possible differences could be very big? But it is also possible the differences could be very small. And is it possible throughout a sample I could have some that are big and small? Yeah, that's very possible, isn't it? And so I'll just give you the formula for that. And I think based on what we saw in the last section, you might be able to at least kind of derive where some of this is coming from. But this is the hard part, and this is the part that hopefully you can help me do this on a calculator. Okay? I already know how, but I need to see if you do. And I'm going to see if you can tell me what all of this actually means when we get done. I don't need you to derive it for me. Just tell me what it says. Whoops. Because there's a big difference between two things in there. And I think you know what n is, right? It's the number of paired data you have. That's a doozy. Standard deviation of the difference. So we're going to take, notice the huge difference between the first sigma of the difference and the second sigma of the difference. Yeah, the first one here says take n, and then it says take the sum of the difference squared. So I'm going to find the difference each time, and I'm going to have to square it each time and then add it up. Here it says minus. Okay, just sum up all your d's and then take that number in. Is it possible those could be two different numbers? Yeah, unfortunately. And I'll show you that in the first example. And then over n times n minus 1, you're probably fairly confident where the n minus 1 is coming from. Yeah. And it says down at the bottom the degrees of freedom are, well, n minus 1. Well, this thing's quite complicated, so I sure hope you can figure out a way to use the calculators to make this go a whole lot faster. If not, the second example is going to take you a while. Yeah. Well, there might be a program out there, but we have to actually be a little bit tricky. We have to be smarter than the calculator on this one. All right, so let's try one of these bad boys. All right. A golf club manufacturer claims that golfers can lower their scores by using the manufacturer's newly designed golf clubs. And I'll tell you a story about golf clubs. That there was actually a study they did, or actually an experiment they did with some professional golfers. 8 golfers are randomly selected, and each is asked to give his or her most recent score. So that's what they did. There's golfer 1 through 8 right there, and their score from their old design, what goes 89, 84, 96, so forth and so on, right? So so after using the new clubs for a month, so they gave them time to adjust to them, The golfers, those same golfers, were then again asked to give their most recent score. So 83, 83, 92, so forth and so on. So realize there's more variables. It could have just been a really bad day or really windy or cold or nice, who knows. The scores for each golfer are given in the table below. Assuming the golfers' scores are normally distributed, is there enough evidence to support the manufacturer's claim? Well, the first thing we should always start with in these, and I know you're probably getting sick of it, is that. And now remember, we are talking about the difference in the mean still. So we're still going to try and kind of figure out, but now do I have to write mu1 minus mu2? Well, no, now it's just mu difference, right? That's what we're saying, right? So mu sub d, we can just write it that way. And so what do we think? Well, we got mu sub d here, and we're saying the difference could possibly be two things. And what is the actual claim? What's going to happen? You lower your score, so in other words, let's see if you can do this. It's going to be in the alternate. Very good. And what am I going to write? That's the tricky part. Nope, no n in there. Ah, why is the difference going to be greater than 0? It changed, and they're saying it went down. So if I shot an 80 the first time and a 75 the second time, if I take mu1 minus mu2, should it be greater than 0? Yes, I'm just trying to get you to see these alternate and null in different ways. So that's our claim. And so what is the other one? Okay, so I'm just having you see it in a different way. So it's saying the difference in the mu's, or mu1 minus mu2, would be that, right? Okay. So let's figure out some information here. What would be helpful to know? Well, what's my main concern is figuring out what's the difference of these things, right? Well, let's find out the difference. And if I were you, I would just write it right underneath. So we are supposed to take this top one minus the bottom one, correct? So what do we get for this first one? We get 6, and then we get 1, 4, oh, negative 2, oh, negative 2, 1, 5, 0. All right. So those are our actual differences, correct? So what is sigma d? Yeah, add up the difference. So we've got what? 11, so 7, 12, I got 13. So then the two things that we might want to talk about is then how do you figure out, this is the big pain right here, is that one. That is the big pain. Yeah, you got to square them, then add them. Big pain. So I'll do that in black. This is 36, 1, 16. Ooh, 4, 4, 1, 25. So that number is 87. Oh boy. Well, that's kind of a pain to do that every time, isn't it? Who wants to do that? Calculator? Well, maybe if you can show me how. So, what do we got now? Oh boy. Boy, just imagine if you had a lot more to do, like, oh, example 3. Boy, that would be a pain to have to figure out sigma d squared. Oh, there is, but we're going to see if we can figure it out. All right, the question was, is there a way to use the list? There is. But we're going to do this problem by hand first, and then we're going to see if we can figure out a way on the calculator. All right. So now, something we might want to figure out is, well, there's a lot of things we could figure out. Let's go ahead and figure out, well, let's figure out degrees of freedom. 7, very good. N minus 1, right? And let's figure out our, I'll just tell you the T critical, because I think we all know how to look that up by now, right? Because this would be how many tailed? Right-tailed, so we know it's going to be positive, right? And I'll just tell you what it is, because I think we're good at finding it out. Not too high, right? This could be interesting. This might get rejected, who knows? And so based on everything, I know it's on the other side of your notes, but what's something that we've kind of been going for first, because it's always that big pain in the rear end. yeah, the standard deviation of whatever you have, right? Like this happens to be the standard deviation of a difference. Oh boy. So we take n, right, which is 8 times, well, good thing that we already figured out this number, right? 87, very good. It's that square. That's that minus, yeah, so we got to take 13 squared, right? Over 8 times 7. Very good. And that is approximately yeah, so let's go 3.07. Does that sound good? That's what I got. All right, so what? So we found out the standard deviation. We got degrees of freedom. We got all this stuff flying all over the place in this problem. But is 3.07 the t-square? Yeah, that's the hard part. Watch out for those numbers. That's why I like this problem, because it came out to be a believable t-square, didn't it? And so I was like, that's 3 standard deviations out. So we should be kind of thinking, yeah, what's going on here? That's quite a bit. So let's go and find the actual standardized test score. Well, how do you do that? What's our little formula? It says to take the average d minus the mean. Well, the mean of d is, we say, 0, right? So we got to find what's the average d. Well, how do you do that? Goodness, there's so much to do here. Yeah, the sum of d, well, we found that that's 13, right? So to find d bar, we take the sum of d, which is 13, and divide by how many we have. 8, because that's the total difference is 13, right? Divide by 8, which is about, I don't know, 1.625. So 1.625 is d bar minus, wait, thinks you got to do that every time, minus whatever we think the mean difference should be, 0. All right. Yep, that's for the population, and that's kind of what we're saying. We like to use that unless we're specified otherwise. And then we got to go 3.07 over the square root of n, which is 8. Because again, we're standardizing it so we can, compare it to something. And we're going to compare it to the 1.415. It's got a little closer than I thought it was going to. When I saw 3 for our standard deviation, I was a little skeptical here. I thought it was going to be way out there. Yeah, 1.5. I got a way closer to that rejection region than I thought. It's a good thing I kept going. I wanted to just kind of say no way when I got there. But 1.5. So is it in your rejection region? What's your critical t-square? 1.415. So is 1.5 in the rejection? Yeah, it is. So you can reject the null, and at a 10% level of significance, you can support the claim. Wow, that was a lot. And let's face it, the hardest part was the standard deviation's hard because you got to take that. Look at all these things you got to find. You got to find d bar, you got to find sum of d squared, you got to find the sum of d, you got to find all this stuff. And again, sum of d squared is the biggest pain in the bunch. Boy, there's got to be an easier way. How would we use the lists? Are we comparing? This is, in a way, a 2-sample t-test, but not really. I'm not trying to compare necessarily the mean from one to the mean, you know what I mean? And so that's kind of weird. So how are we going to go about this? Because I want to really compare, I want to talk about what? I want to talk about the difference. You could do that. Very true. We could sit there and find the difference every time, right? And make that a list. We could make a list of 6, 1, 4, -2, negative, all that, right? No, there might be. No, we don't want, we actually are going to try and make this a 1-variable test. So we're trying to use a t-test, not a 2-sample. So let me show you something that's pretty slick with the calculator. It will do some calculations in the lists for you. Okay, so let's go in there and let's go do our, and everybody can see it. I should probably move it over. So let's go clear out at least list 1 and list 2, all right? Well, and list 3. So let's clear list 1. Let's see if this will work. I don't know if it will. Oh, cool. Clear list 2. And I bet you there's a way to clear them all, isn't there? And I'm sitting here doing them all separately. Done. Actually, I know there's a way, but it takes a lot of...
Yeah, you can just put commas.
Can you? Cool. So let's clear all those out. And let's go in and, oh, there's L1. What do you suppose we're going to put in L1? We're going to put the scores for the, well, you could put the difference in, but let's say these were numbers I didn't really want to mess with. Big numbers, or there's a lot of them. I don't want to find them all. Yeah, let's just enter all the scores for the old design. 89, 84, 96, 82, 74. Well, that's a good golf right there. 92, 85, 91. Everybody agree with that? Here's something you can do. You just kind of go back up and then go just over to list 2. Oh, does it go right to the top for you or no? Oh, sweet. All right, so then let's put list 2 in. 83, ooh, 83 again. 92, 84, 76. 91, 80, 91. Got it? So there are your 2 scorer lists, right? That seems like it took a lot, right? Any idea how I can make the calculator make L3 the actual difference? Wait, before you do that, go up so L3 is highlighted. See, it says L3. What do you want it to equal? Well, I would like it to equal L1 minus L2. That's what I want it to be, right? I could say take L1 times 7 if I wanted to, right? But that doesn't help me in this problem, right? But I can just say, okay, take list 1. Does everybody see where they are? They're above like 1, 2, 3, all those. L1 minus L2. Boom. Yes, this would have done a lot of your first couple of chapters for you, but you needed to know how to do it by hand. And let's face it, we found a better way now anyways, using the 1 variable test, so it does it faster anyway. All right, now what? You could, but that's a great idea. Take list 4 and say take that number and square it. You can actually do that. Say take L3 and take it to the second power. Then we would have all those numbers, right? But then how do you take that list back out? And you could write it down, right? You could have it sum it too, right? You could do that. That's one of your options, sum that. But that's still, then you go back to these formulas, right? We could use this as data, can't we? We can use L3 as data. For what kind of test? We can do better than that. Let's do a t-test. So let's go over. Yeah, we could do the 1 variable stats on it, right? It could give us a lot of information. But then we'd still have to get d squared, right? And so still, it doesn't really avoid that part that is a problem. Because it's a pain. All right, I'm going to sit there and tell you it's a pain. So let's go over, let's just do a t-test. But do I really have, do I want it to look at 2 samples here? No, I just want it to look at the difference. All right, so t-test. Well, I don't want to do stats, I want to do data. So let's say the mean is 0. Yeah. And yeah, list 3, very good. If you leave it as list 1, is that going to work out for you? No. Well, it'll give you answers, right? But not what we want. So we're going to put list 3 there because that's what we have the difference. And yeah, it's a right-tailed, so we better fix that, right? So we got to go over, right? And how come it's not asking me the pooled thing this time? Yeah, it's just one sample, right? I'm not taking two different things here. And we can draw, calculate, whatever you want to do. Oh, t is 1.498. Oh, we got 1.5. How about that? P-value is 0.08. So it's saying there's an 8.9% chance that this would happen. What was our level of significance? 10. Oh, P is less than alpha. Reject. Okay. But notice, hey, X bar, did we find that? Really, that means what here, though? That means D bar, right? Okay. And there's our 3.07 that we got. But you see, it still doesn't give you that thing squared. And so if you wanted to do it by hand, it is not going to get you any better. But this just does all the work once you get the lists in there. Okay? So do we still reject based on this knowledge? Yeah, we do. But again, the one thing it doesn't give you is the T critical value because it doesn't know which one you're testing. That's why it gives you P. It says, I know what the probability is here. What's the probability you want to be? Now let's say if they said a 5% level of significance, then we couldn't reject, right? But seeing they said 10%, we can reject because that's 8.9%. Okay? Yes? Nope, because all that is that it was ran out of room. That's just the same 16 people doing 2. So for tomorrow, your job is to get a calculator and do example 3 and tell if you can reject or not. And, you know, I don't need you to do it by hand necessarily unless you want to. But realize you'd have to square all of those differences, and one of the differences is 24. So good luck on that, okay?